Okay, so we'll do this one more time, looking at the maximum expected returns portfolio. So just a little bit of a reminder about the problem I'm trying to solve. I have a vector of portfolio weights, W, that I think of as, so I'm thinking of n assets in my portfolio. So W1 is the amount of my portfolio invested in asset 1. W2 is the amount of my portfolio invested in asset 2, and so on. There's n assets in the portfolio. And there's a constraint on this vector W that the sum of the elements has to be equal to 1. So I sort of have one chunk of money that I'm going to use to buy my portfolio. And so the sum of all the pieces I put together to make that portfolio will end up equaling that 1. Then for each of the n assets I'm going to put in my portfolio, I have a value mu1 that's the expected return of that asset. I'm going to put all of those together in a vector and call that mu. And then I also have a covariance matrix for the returns of the asset that I'm going to call sigma. And so this has to be an n by n matrix because it needs to tell me the variance of each asset. So it has to have n diagonal elements. And then all of the off-diagonal elements are going to tell me the covariance between that particular pair of assets. So whatever asset corresponds to, say, row I and column J. And this has some special properties. So it's symmetric. That means sigma is equal to sigma transpose. And it's positive definite. So this means that if I take an eigenvalue decomposition of sigma, all of the eigenvalues are greater than 0. And the problem I want to solve, I want to maximize the expected return subject to the constraint on risk. So the expected return for each asset is mu sub I for asset I. And so if I just multiply that by the weight of each asset and sum that up, so you can think of that as just the dot product of mu and my weight vector W, which I'll write in matrix notation as mu transpose W. I want to maximize that quantity. So again, this is going to be a linear quantity because these mu's are given to me, and then the w's are just all to the first power. So this is going to be mu1 is the coefficient times w1, mu2 is the coefficient times w2, and so on. And then I have two constraints. So there's the linear constraint. So E transpose W has to equal 1. So remember, E is a vector of 1s. So this is going to be on the final too. I use E as a vector of 1s. So just to keep that in mind. So E transpose turns that into a row vector times a column vector W. That's the same thing as just the dot product of E and W. And since E is all 1s, that's just the same thing as the sum of the elements of W. And that has to equal 1. So that's my constraint on the portfolio weights. And then the second constraint is W transpose sigma W. And so this is interpreted as the risk of the portfolio. And the optimization I'm trying to do is subject to my portfolio having a certain level of risk. I want to choose W to give me the maximum possible expected return. So that's what this optimization problem is asking you to do. So we say it has a linear objective. So that means all of the W's are all to the first power. And then it has linear and quadratic constraints. So this is the linear constraint, and then this is a quadratic constraint. And I can write out the Lagrangian for this. So it's going to be a function of W and lambda. So here lambda, because I have two constraints, lambda is going to be a vector with two elements. So I have lambda 1 and lambda 2, the Lagrange multipliers. And then it's just equal to the function that I'm trying to find the optimal value of. So that's the objective function. Plus lambda 1 times the first constraint, plus lambda 2 times the second constraint. Then I need to take the gradient of the Lagrangian. So this is what I want to set equal to 0. So I want to find the inputs W and lambda that are going to make the gradient of the Lagrangian equal to 0. That's going to give me the critical points of the Lagrangian. So this is actually a little bit prettier because we can assume some knowledge of the problem. So in the last problem, I had to write out this huge matrix pretty much element by element. Here, because I can write everything in terms of this mu vector and the covariance matrix, it saves me a little bit of notation. But you have to be careful about the dimensions of things to make sure that they add up. So this is a gradient of a function. So the Lagrangian is a function of, so this would be n plus 2 variables. And it's a scalar valued function. So when I take its gradient, I'm going to get a row with n plus 2 elements. So you want to make sure that at least there's n plus 2 elements over here. So this will be the first portion of the gradient, the second portion, and the third portion. So what is the dimension of this? Well, mu is a vector of expected returns, and there's one expected return for each asset. So mu transpose is just going to be a row vector of n elements. Then I have lambda 1 is a scalar value. The E transpose, so E is a column vector of n ones. So E transpose will be a row vector of n ones. And when I multiply that by lambda 1, this thing that I have highlighted here, that's going to be a row vector that just contains the value lambda 1 n times in a row. And so since this is a row vector with n elements, and this is a row vector with n elements, I can go ahead and add them. And then I just need to make sure that the last thing here is also a row vector with n elements. So 2 lambda 2, that's going to be a scalar quantity, so I don't have to think about that. Then I have W transpose sigma. So W is a column vector with n elements. So if I take its transpose, it's a row vector with n elements. So its dimensions are 1 by n. And sigma is an n by n covariance matrix. So if I have a 1 times n vector times an n by n matrix, that's going to give me a 1 by n output, which is again a row vector of n elements. So I can sum up these three terms, and that's going to give me one row vector with n elements. Then here, for the second part of the gradient, I have E transpose W. So that's just going to be a dot product. This is a single row times a single column, so that's a scalar quantity. And then when I subtract 1, that's also a scalar quantity. So this is 1 by 1. And then W transpose W. So again, this is a bit tricky, but this W transpose is 1 by n. Sigma is n by n. And W is n by 1. So it's always the outer dimensions that are going to determine the dimension of the product. So this starts with a 1, and this last W ends with a 1. So this quantity that I have highlighted is a 1 by 1 quantity. So that's just a scalar value. And then sigma squared p is the risk of my portfolio that I'm stating. So that's also a scalar value. So this final part of the gradient is a scalar value. So my gradient is 1 by n plus 2, which is exactly what I was shooting for because I have n plus 2 values as inputs for my function. So I want to solve to find the critical point again. So I'm going to define my function g to be a function of w and lambda. It's just going to be the transpose of this function of the gradient of the Lagrangian. And so I end up with this vector here that I want to set equal to 0. But again, it's got this quadratic form in it. So it's not going to be something that I can just solve as a linear system. So so it's going to be a nonlinear problem that I need to solve. So I'm going to have to approach this with Newton's method again. And so the first thing I'm going to need is this function g. And then the second piece to be able to do my Newton iterations is I need the gradient of this function g. And so again, this is quite a bit easier to write down than the previous example because I know a little bit more about the form going on here. So I can just take the gradient of this function is going to be the derivative of this with respect to w, then mu1, and then mu2. Or sorry, w, and then lambda1, then lambda2. So if I take the derivative, mu is constant, so when I take this derivative with respect to w, I get 0. There's no w here, so that also becomes 0. But there is a w here. And so it turns out that when you take the derivative of this is actually a matrix product. So this is going to be, so it has n pieces. So it has n rows and one column. So when I take the derivative of that, I'm going to end up getting a matrix. So this quantity here is 2 times lambda 2 times sigma. So this has the same dimension as the matrix sigma. So this upper left block is n by n matrix. Then when I take the derivative of this with respect to lambda 1, I'm just going to get e. So that e is going to go here, except remember e is this column vector of n ones. So at least the dimensions match up. This has n rows. This has n rows. And then we've also talked about taking the derivative of a quadratic form. So the derivative of this is 2 times sigma times w. So this is also going to be a quantity with n rows. So this top row that I have written here, if I were actually to write out every single element by itself, this would have n rows and n plus 2 columns. So then when I take derivative of the second line with respect to w, I just get E transpose. And since there's no lambdas anymore in here, the bottom right block is always going to be 0. And so then again at the bottom here, I take the derivative of this quadratic form, and that's what's going in here. So now I now have the pieces. I'm going to go through an example from the textbook now. So they used 5-asset example with expected returns of 0.8 through 0.20. And the asset returns covariance matrix of this. So remember that these things are sort of on the order of mu squared. So that's why these are going to be so much smaller than what's going on here. And then the target risk was 25%. So the sigma squared p is going to be 0.25 squared, which is 0.0625. So this was the definition of the function g of w and lambda. And so I can write an R function to compute this. So again, I'm going to use this vector x is going to be w, and then the last two elements are going to be lambda 1 and lambda 2. So x, if w has n elements, then x is going to have n plus 2 elements. And now, instead of hard coding the values for mu and sigma into this function, I want to also make them arguments to my function, so that if I wanted to solve another problem with this same function, instead of having to rewrite the entire function, all I have to do is make a new vector mu and a new matrix sigma, and then I can just pass those in as arguments as well. And then I also need this sigma p2, that's just this value here, which is the constraint on the risk of the portfolio. And all I'm going to do is just evaluate, I'm trying to highlight the top line here, but it doesn't seem to be working. I'm going to just evaluate these 3 pieces one at a time and put them into a vector and then return that. So that's all the function g is going to do, just return the vector value of this function g. And so the first is just mu plus, this is just going to repeat lambda 1 n times, which is exactly what this second term in the first row is doing. And then 2 times lambda 2 plus sigma times w, so that's just what the third portion of the first line is doing. E transpose w, that just sums up the values of w. So I'm just going to use R's sum function to do the same thing. And then W transpose sigma W minus sigma squared P. So there's W is the first n elements. So I guess I was a little bit sloppy here, that 5 I should have used an n, but because this is a 5 by 5 example, I had a 5 in here in the first place. So I have W transpose. So in R, this T function transposes. So W transpose sigma W minus sigma squared P. And I'm going to use the C function to wrap all that up into a vector and return it. Then similarly for the gradient, so this is again going to be a little bit messier than the last one. I'm going to use pretty much the same approach I used in the previous example. So I'll make grad, which is a matrix of zeros, has dimension n plus 2 by n plus 2. Then in the top left n by n block, I'm going to put 2 lambda 2 sigma. So 2 lambda 2 is scalar. Sigma is an n by n matrix, so that's why I have to assign it into an n by n block of this matrix grad. And I just have 2 times lambda 2 times sigma. Another nice feature of R is if I assign a scalar value into a range in a vector. So here I'm assigning the number 1 into columns, or into rows 1 through n of column n plus 1. So that's referring to this E up here. It's just going to repeat that 1 enough times to fill up that range. And so the same thing's going to happen for this E here when I run this command. And then for rows 1 through n in column n plus 2, so that's describing this portion over here, I just need to put 2 times sigma times w. So remember, w is the first 5 elements of the input to this function. And then again, I put mu sigma and the constraint in here, just so that I can change this anytime when I want to use it to solve a different problem, so for a different mu and a different sigma. And I guess this is a little bit over-parameterized, since I don't think mu and the constraint don't show up in here. But I just wanted to use the same arguments as I had for the function g. So then the Newton, so once the bulk of the work was getting these two functions to compute the gradient and the function. But once I've done that, I can just assign myself a starting point. So I'm going to use 1/2 repeated 5 times. So this is going to make a vector just 1/2, 1/2, 1/2, 1/2, 1/2. Then I'm going to put a 1 and a 1 at the end of it. So my starting point is 1/2 for x, or for w1 through w5, which I don't know how much sense that makes, because the one thing I do know about the w's is that they should sum up to 1, but at least it works. And then I'm using values of 1 as the starting points for the 2 Lagrange multipliers. So that just looks like this. My Newton iterations, again, this part's almost always going to be the same. I compute my gradient, and I compute my function, and then I just need to solve that linear system. And then I use that to update x. So I'm writing the updated x in the same piece of memory as x had. And I'm going to repeat that 25 times. And that gives me this computed solution here. So I couldn't quite fit the whole w vector on the first line. So this first 5 parts correspond to w1 through w5, the portfolio weights, or the asset weights within the portfolio. Then this is the first Lagrange multiplier and the second Lagrange multiplier. And then I'll do the same thing I did last time to try and classify this as a minimum or a maximum. So one of the nice properties about the minimum variance portfolio is because I had to solve a linear system to get the critical point, I know there's only one critical point. Here, I'm not certain what critical point I got. If you knew a little bit more about the problem, there should actually be two critical points. And it turns out that one of them corresponds to the portfolio you want, and the other one corresponds to the absolute worst portfolio you can get according to your constraint. So it is important in this one to be able to classify the point you found as the actual maximum. So we'll go back and look at the upper left n by n block of the gradient of the function g. So this is actually just going to be the transpose of the Hessian of this function of the Lagrangian, so f, except when I plug in the computed values, lambda c.
What are your values on your weights with -0.4? That's just
Yep.
Is that just a non-realistic outcome, or is there a meaning?
No, you can actually do that. So what that corresponds to is something called a short sale. So what I do is I pretend like I don't have any shares of Starbucks, but I borrow some shares of Starbucks from some guy who does, and I sell them to you, so you give me money. And then, yeah, so there's a negative weight means I owe that guy some Starbucks. Yeah, and I have to buy that back in the future to give it back to him. So you can actually do that. Yeah, the problem gets to be a bit more complicated if you start putting extra constraints on it, like the W's have to be positive, so, which can be solved, but not in the very first math class that looks at that sort of thing. Oh, oops. So this is the matrix. So last time I set up the problem, or not me, but Dan Stefanica, who is the author of the course textbook, set up the problem so that this matrix was diagonal no matter what. So he set up the Lagrangian so that the off-diagonal elements were always going to be 0. Here, that's clearly not the case. So since the matrix isn't a diagonal form, you need to compute the eigenvalues of this matrix. And the computed point, so W sub c, it'll correspond to a maximum if this matrix is negative definite, and it'll correspond to a minimum if this matrix is positive definite. And so the way we can check that is, because this is just a matrix, it's just numbers, I can just compute the eigenvalues of that. So I use eigen to calculate the eigenvalues. This is just the code to generate this matrix here. And then the $sign says it. So the eigenfunction will also give me the eigenvectors, but I'm not really interested in that right now. So if I take just the values out of this function, I get this vector of 5 values, and they're all less than 0. So that tells me that this matrix is negative definite. And that tells me that the computed point, x sub, or in this case, W sub c, corresponds to a constrained maximum of the objective function. And then finally, I can find the computed W. So that's 0.199. And so this is the maximum that I can make the expected return for my portfolio, subject to having a risk of 0.25 squared. Okay, so that's all oh, okay, yeah.
On those, how did you know, because you just did 25 iterations, so how do you know that you actually have a critical value after 25 iterations?
Yeah, just to make the stuff fit on the slide, I did that. Really what you should do, so remember that this was in the section on doing Newton's method with vector-valued functions. This is sort of my update. And so what happens is, if it works, it's supposed to be converging to a certain value. So converging means that my current estimate is close to the thing that I'm trying to get. And so when I'm in that situation, if I update, I shouldn't move too much. And so what you can do is you can monitor the norm of this vector. And when that gets below a certain level, and usually you want to do it relative to the size of x. So you could say the norm of this vector divided by the norm of x. When that's less than, say, 1 in a million, then you just say that this point is so close to x that I'm going to stop. So you need to kind of think about it a little bit. But essentially, you want to define a value somehow of what it means to be close enough to the thing you're trying to get. And then you just watch as you're going along. And when you hit that, then you stop. But like I said, Newton's method isn't really guaranteed to converge. So it's also good to have something like this, like you go 50 times until you stop. So you'll either stop or you'll hit 50. But if you don't put a maximum number of times and it doesn't converge, it's just going to keep going and going and going.